All right. Excellent. So welcome to the 1W-MINDS seminar for this pretty nice, even in Michigan, March 2nd seminar talk.
Oh, it's March.
Yeah, yep, it is. Today we have the pleasure of having Professor Yuejie from the Electrical and Computer Engineering Department at Carnegie Mellon University here to talk to us about the non-asymptotics of reinforcement learning. Professor Yuejie is the inaugural Robert E. Doherty Career Development Professor in the ECE department at Carnegie Mellon, and has a lot of really interesting paper and research interests in theoretical and algorithmic foundations of data science, machine learning, signal processing, and inverse problems. So a lot of nice applications to imaging, decision making, and a whole bunch of other things. So it's my pleasure to have her here to talk to us today, and I'll turn things over to you. Looking forward to it.
Thank you so much, Mac, for the kind introduction. I'm sorry I have made a typo on my slide. I didn't realize it's March already. Time just flies. So I'm very happy to talk about some of our recent work on reinforcement learning. This is a new research thread that I have initiated in the last maybe 3 years in my research group. And I'm very eager to share some of our findings with you today. And this line of work is joined with a bunch of collaborators, students, from my group and the UPenn, particularly Yuejie Chen and Yuejie's group. So what is reinforcement learning? Probably many of you in the audience are not very familiar with this concept already. This is kind of a machine learning paradigm where the agent tries to learn by interacting with the environment. And we've already seen a lot of success stories of IL that hits the news, from the early news of achieving superhuman performance in the ancient-old game Go to more recently, beating human in games like poker, StarCraft, and even helping us to design AI chips. So it's probably not an exaggeration to think IL holds a lot of promise in the next era of artificial intelligence. However, to make IL really work in practice, there are a lot of challenges to train IL agents properly. One of the probably most well-known challenge is this dilemma of exploration or exploitation. Because typically the agent only have limited resources, it has to make a decision whether to rely on the current information about the environment and to exploit the current knowledge, or actually use the resource to explore unknowns with the hope that it can actually find a better strategy. There is also an issue called credit assignment problem. This is because in a lot of these problems, the agent is actually interested in maximizing the total long-term rewards, but not just the immediate rewards. And in a lot of real problems, the reward we're receiving from the environment, it typically is delayed. So it is actually quite challenging to figure out what is the right action to take due to this kind of delayed rewards or feedback. Moreover, many of the problems we are facing in modern era has huge dimensions in terms of both the state space and action space, making designing these problems very challenging in terms of computation or sample efficiencies. From an optimization perspective, a lot of the problem can be solved as some kind of value maximization problem, where the optimization landscape can be highly non-concave. So all this makes the problem very challenging to deal with. In today's talk, I'll be primarily interested in understanding the efficacy of reinforcement learning algorithms. Particularly, I'll be interested in looking at both the sample efficiency and computation efficiency. The reason I'm interested in looking at the sample efficiency is because in a lot of the problem we are dealing with in practice, in scenarios where we think reinforcement learning might be relevant, collecting data samples can be very expensive or time-consuming. So we really want to have reinforcement learning algorithms that can be sample efficient, that can learn a good policy using as fewer samples as possible. In addition, I also care about computation efficiency. If you look at a lot of the success stories of reinforcement learning these days, many of these algorithms take a lot of time and space to train. You need a lot of CPU, GPU, or even TPUs, and run them for many, many computing hours before you can land on a good strategy. This may not be readily available for maybe a frugal person like me who doesn't own a lot of GPUs. So in order to make our really be broadly applicable, we also want to design computationally efficient reinforcement learning algorithms that can hopefully converge using fewer computation resources. So with this in mind, let's look at a little bit of, from the maybe theoretical perspective, the development of our theory from maybe a high level perspective. Reinforcement learning is actually not a new topic. If you go back to maybe the 80s or 90s, we already see a lot of landmark results in the literature, maybe primarily from the control community. But most of the analysis back then are sort of asymptotic in nature, meaning they look at the convergence of the algorithm, whether they can find the optimal policy if you are given an infinite number of samples or an infinite number of iterations to execute these algorithms. This type of asymptotic analysis is nice because it gives us kind of a comfort that the algorithm at the end of the day can find the optimal policy, but they may not be necessarily sufficient in the modern era where we have very large scale problems and we really don't have infinite number of samples or infinite resources to execute these algorithms. Rather, people have shifted the paradigm to look at the so-called finite time or finite sample analysis, leveraging a lot of the advances in high dimensional statistics and high dimensional probability. So the idea being you might have two different algorithms, both converge asymptotically, but they could be converging at drastically different rate, which can only be implied by examining them through this kind of finite time non-asymptotic lens. And that will be the focus of the approach I'll be taking in today's talk. And in fact, I think non-asymptotic analysis for reinforcement learning are sort of the key to understand the sample and computational efficiency in the modern era. So that will be our focus today. And particularly, I want to examine three distinct type of approaches in reinforcement learning, value-based, policy-based, and model-based. In three different algorithm settings. In value-based approach, I'll look at the classical algorithm of Q-learning and try to understand whether this algorithm is minimax optimal. In policy-based approach, I'll take an optimization perspective and try to understand the finite time convergence rate, some of the popular policy optimization algorithms. Finally, I'll move to offline reinforcement learning, which is a emerging IL paradigm that tries to learn optimal policy by only using history data without active exploration by examining a model-based approach. At the end of the day, the question I'm trying to answer is, does reinforcement learning learn the optimal policy? And if it learns the optimal policy, does it learn it in an optimal manner? All right. Before I jump into looking at these algorithmic approaches, I'm going to first introduce a sort of a mathematical model that sort of based on which we are going to develop reinforcement learning algorithms. And this is the so-called Markov decision process, which I think many of you are probably very familiar with. But just to make sure everyone is on the same page, let me introduce this model very quickly. So this Markov decision process, or MDP for short, is a classical or standard model to model this closed loop interaction between an agent and the environment. And we're going to model configurations of the environment using some kind of state space, which is assumed to be a finite set in this talk. And we're also going to model actions that are going to be taken by the agent as from some sort of action space, which again is also going to be modeled as a finite set. But both of these sets can be potentially very large, modeling high dimensional problems. Upon seeing an action from the agent, the environment will push a reward to the agent, which is a function of both the current state and the current action, which is going to be assumed to be normalized to an interval from 0 to 1. the goal of the agent is to try to come up with a policy which tells the agent how to make decisions. So the policy is actually a probability distribution over the action space for any given state. So for any configuration of the environment, the agent will try to select an action according to the distribution of this policy. So this is also sometimes also called the action selection rule. And if you have a deterministic policy, it can be easily subsumed also in this case by just making this distribution a singleton. Finally, after one round of interactions, the environment will actually be changing. So the next configuration of the environment will be drawn from this probability distribution over the state space for the given current state and the action of the agent. And the system will basically looping over and over according to these configurations. And the goal of the agent is trying to design policies. And in order to make this well posed, we want to know how we can actually evaluate the goodness of a policy, which comes to the definition of these value functions. So imagining I'm initiating the environment as some initial state as 0, and then I'm rolling out a sequence of actions according to this policy pi, and along the trajectory, I'll be collecting a sequence of rewards. So the value function will be defined in this kind of infinite horizon setting as a discounted total sum of all the rewards we are collecting on this trajectory, averaged over all the randomness in the problem. What is interesting or important here to note is this parameter gamma, that is a number between 0 and 1 called the discount factor. And roughly speaking, this means I'm going to put higher weight on my immediate rewards than the future rewards. In most of the problem we care about, this parameter gamma will be very close to 1, indicating that we're actually modeling a long horizon problem. And roughly speaking, you can think of this number 1 over 1 minus gamma as the effective horizon of the problem, so that after this effective horizon, essentially rewards you accumulate after that carries minimum value to you in your calculation of the value function. Another very important quantity is a Q function, which is defined very similarly as a value function, with the exception that I'm going to actually allow myself to take the first action arbitrarily and then follow the policy pi to take the rest of the actions. So the Q function is actually a two-dimensional function defined over both the state space and the action space, while the value function is only defined with respect to the initial state. And you'll see later, both of these are very important in the development of reinforcement learning and the dynamic programming in general. So with these definitions in place, we can write out the goal of the problem in MDP, which is basically searching for the optimal policy pi that maximize the value functions. And if we know the models, this is a well-studied problem in the literature, dynamic programming, and goes where we know the optimal solution can be found by essentially the Bellman's optimality principle. While in reinforcement learning, what people care about is how to solve this problem when we actually do not know the model configuration, particularly when the environment is unknown to you, how you can actually solve this problem, finding the optimal policy in a data-driven manner. Notation-wise, in this talk, I'm going to put a star for all the quantities that are optimal. So I have V star, Q star, pi star indicating the optimal value function and Q function and the optimal policies that I'm interested in finding in the problem. All right. So is the problem clear to everyone so far? Okay. So as I mentioned, if we know the model exactly, there is this actually very well established Bellman's optimality principle that allows you to find the optimal policy. And this actually serves as an entry point for us later to talk about reinforcement learning algorithms. So at the core of this Bellman's optimality principle, we'll have this Bellman operator, which essentially tries to map some kind of Q table, Q function table, to a better estimate based on this one-step look ahead principle. And what we know from Bellman is that in fact, the optimal Q function, which is a Q function for the optimal policy, is a unique solution to this Bellman, is a unique solution, a unique fixed point to this Bellman operator. And what we also know is that this Bellman operator has a very nice contraction property that if you take a pair of Q table and you look at the entry-wise error between them after applying this Bellman operator, this error actually contracts as a rate of gamma, where gamma is a discount factor. Because of this fast contraction, this allows us to actually find the fixed point of the Bellman operator using very efficient algorithm like policy iteration or value iteration, both of which actually converge very fast. So this kind of give you a little bit, just a very quick overview for some of the background information about the MDP problem in the dynamic programming literature. And hopefully with that background in mind, we can now jump into our discussion about some of the reinforcement learning algorithms. And as I promised, the first algorithm I want to look at is Q-learning. And I particularly want to look at whether this algorithm is min-max optimal or not. So in order to talk about min-max optimality and sample efficiency, I also need to tell you where the data come from. For the purposes of the talk, I'm going to only look at this very simple model called the generative model or simulator. In our paper, we also look at more realistic model, like when you have Markovian settings. But in this generative model, the nice thing is that this gives you a mechanism to actually query any state action pair in your problem. And this generative model will pop out the transition, tell you where the system will go next based on the transition kernel. So this gives you a way to sample from the transition kernel without actually seeing it. And so it's, although it's kind of a contrived model, but it does have some value in practice for problem where you maybe you know the underlying dynamic and physics, but you cannot write down the transition kernel, but rather you can sample from it very efficiently. From the theory perspective, it also has a nice benefit that this allows me to essentially explore the entire state action space. So I only need to worry about the issue of exploitation. So I somewhat bypass the issue of exploration and exploitation trade-off by looking at generative model, but still I have the question remaining in terms of how many samples do I need in order to learn the optimal Q function, both in terms of necessity and sufficiency. So we want to look at this problem for understanding Q-learning when we think of data coming from the generative model. And Q-learning is this very popular and classical model-free algorithm in reinforcement learning, which really just tries to do stochastic approximation for solving the Bellman equation we just mentioned. Because we do not have access to the model, so we can't really directly evaluate this Bellman equation because it actually uses a transition kernel here. Rather, we're going to rely on some kind of stochastic version of it based on samples. So in every iteration, I'm going to say I can actually draw from the generative model for all the state action pairs and see one transition for each of the state action combination. And based on the transition I see, I can construct the stochastic version of the Bellman operator, this TT, which simply replaces the next state by the actual sample that you see from the transition. And because this TT is much more stochastic than the population version, so when I try to update my Q function, I will not completely rely on the stochastic draw, but I actually only take a more conservative step by taking a convex combination between the previous Q table and the new update based on the stochastic data I collect. And this eta t is some learning rate I'm going to select later. So this gives you the most simple variant of the Q-learning algorithm called the synchronous Q-learning algorithm, because we are simultaneously updating all the entries of the Q function, leveraging the generative model. And the natural question is then, how many samples do we need if we want this synchronous Q-learning algorithm to produce a good Q function estimate, maybe up to some epsilon accuracy in terms of L infinity error. Obviously, this is not a new problem and has been studied a lot in the previous literature. Just to sample some of the landmark results in the literature. So to the tightest sample complexity we've seen in the previous literature from this paper by Wainwright et al. And Chen et al. A couple years back. And they essentially pinned down a sample complexity, which is on the order of SA divided by 1 minus gamma to the 5th order times epsilon square. Well, we also know from the literature, if you don't care about what algorithm you use, the minimax lower bound for this problem actually scales on the order of SA divided by 1 minus gamma to the 3rd order times epsilon square. So if you compare this upper bound with this minimax lower bound, especially in terms of dependency with the effective horizon, we see there is actually an interesting gap where all the prior upper bounds has a dependency on the 5th order, while the minimax lower bound only has a dependency on the 3rd order. So the natural question is, does this mean Q-learning is inherently suboptimal? Or is this an analysis artifact that people just haven't tried hard enough to tighten the upper bound? So with this question in mind, we actually take a first step trying to sharpen the sample complexity analysis. And we actually had this result that we were able to tighten the sample complexity a little bit by showing that for an accuracy range from 0 to 1, the sample size essentially scales on the order of SA divided by 1 minus gamma to the 4th order times epsilon square. So this indeed improves the upper bound by a factor of the effective horizon. Now we have the 4th order instead of the 5th order. And this result holds for both if you're using a constant learning rate or using the so-called rescaled linear learning rates. Both are popular choices of learning rates that people are using in practice. So at this point, it seems that we are still left with some work to do because we are still one factor away from the minimax lower bound, which scales with the horizon on the 3rd order, right? And it turns out that it seems empirically there is strong evidence that we cannot improve this dependency further. And this can be seen using some toy examples that is extremely simple. So this is an example we actually took from the paper by Martin Wainwright, where he had this very simple example that only have 2 states. And what happens at state 1 is that we have basically duplicated what happened as a consequence of some actions. So essentially, if you look at the 2 actions at state state 1, the red one and the black one, they have exactly the same consequence with some carefully chosen parameters. And for this very simple toy example, and it turns out that if you run this Q-learning algorithm empirically, the sample size indeed scales with the effective horizon on the 4th order. So this seems to be suggesting Q-learning is inherently not minimax optimal. And based on the evidence from this toy example, we actually also develop a algorithmic dependent lower bound that is tailored to Q-learning, where we actually construct this counter example, this toy example, and show that if you want to drive the error to be, say, epsilon, to some order of epsilon, then Q-learning will need at least a number of samples that scale on this order, SA divided by 1 minus gamma to the 4th times epsilon square. So this is actually the exact construction in the paper is inspired by the toy example, but a little bit more complicated just to facilitate analysis by adding in some auxiliary states. And this result is interesting because it's not a minimax lower bound, but is a tailored algorithmic dependent lower bound just for Q-learning. And if you put the upper bound and the lower bound together, we now essentially have a matching lower and upper bounds for Q-learning that pins down the sample size requirement for Q-learning on the order as A times the fourth order of horizon divided by epsilon square. And it actually has this provable gap from the minimax lower bound, indicating Q-learning is actually not minimax optimal. And in fact, we know if you take a model-based approach from the literature, we know if you take a model-based plug-in approach, that is, you first empirically construct the model and then run dynamic programming based on the estimated model, that algorithm actually achieves the minimax lower bound. So this seems to be suggesting, at least for this vanilla version of Q-learning, this model-free algorithm requires more samples than a model-based algorithm because of this gap. And let me just comment on a little bit more about why Q-learning is suboptimal. And this is actually an issue that people have observed even back when Q-learning was first proposed as known as the issue of overestimation of Q-learning. So roughly speaking, what happens is when we're replacing the population Bellman operator by its sample version, we are replacing this expectation of some quantity by its empirical estimates. And due to nonlinearity in the Bellman operator for this action selection in this maximization operator, this tends to get heavily overestimated or having high positive bias when you try to replace the expectation by its empirical estimate, particularly when you have a small sample size. And because of this overestimation, you will need to have more samples to overcome it later on, resulting in the sample inefficiency of Q-learning. And this issue is also observed in the more recent literature of deep IL, where there's actually interesting evidence as shown on the right figure here that I copied from a paper from DeepMind, where they actually show this overestimation issue gets more severe if you have more actions. So what they were doing is they essentially try to do something similar to the toy example I showed, but they do it with more actions. So instead of 2 actions, you can increase the number of actions to 4, 8, and so on and so forth. And you see the overestimation error as shown in these red bars essentially gets worse. And in fact, they introduced this new algorithm called double Q-learning that probably has a smaller error. And that algorithm is very, very popular in the deep IL literature. So it's actually an interesting open problem to see whether people can develop tightened sample complexity bounds for some of this new variants of Q-learning that seems to have better sample efficiency in practice. All right, so that sort of covers my discussion about Q-learning. I wonder if there are any questions before I jump to policy gradient methods. Since there's a question about continuous state action spaces, is there a lower bound? I think it might be possible if you do maybe, but maybe I think you may need to do some kind of non-parametric methods in order to do that. I'm not aware of an existing result on the lower bound on top of my mind, but I think it's probably possible. It's also possible to address continuous state action space using function approximation. And I think there are also some lower bound results in that regard as well. All right. So let me now switch gear a little bit and then talk about some of the policy gradient methods. So this part will be more optimization oriented, unlike the previous part that's more statistical in nature. So what is policy optimization? This is a slightly different approach that people take in reinforcement learning, trying to leverage a lot of the advances in large-scale optimization. So you can think of reinforcement learning as an optimization problem where you are trying to optimize a value function, which is parameterized by some policy. And the policy is maybe also parameterized by something else. And then you can actually run maybe gradient type methods on top to optimize the underlying parameters by computing gradient of this objective function. And the benefit of taking this optimization view is this really allows you to have very flexible ways to integrate different kind of parameterization of the policy, where you can have both continuous decision variables and also discrete decision variables all at once. It will also allows you to take in some of these more recent advances in deep learning by thinking about parameterizing the policy using deep neural networks. And then running policy gradient will be similar to just running backprop on your neural networks. So because of these reasons, policy gradient methods have been very popular in practice. And the question from a theoretical perspective is, can we actually understand the global convergence properties of these policy gradient methods and even think about how to accelerate their convergence? So just to put the method in a little bit more mathematical footing, let me just introduce a little bit about the formulation we have. So as I said, we need an objective function, and we're going to get this from the value function. And earlier, we're defining the value function in a per state manner. And the easy way to get an objective function is just to crash all this per state value function into a single function by averaging over the state using some state distribution, initial state distribution rho. And a popular way to parameterize the policy, as has done, is using the softmax parameterization, kind of like what you use in a multi-class classification problem. And the nice thing about this is you can now actually have an unconstrained optimization problem over the parameter theta. Unlike earlier, if you're optimizing directly over the policy, it's actually a constrained problem over the probability simplex. So now with this unconstrained optimization problem in place, we can run policy gradient methods, which simply tries to update the parameter theta by searching along the gradient direction of the value functions with some learning rate. For simplicity, we're going to assume this gradient can be evaluated perfectly. For example, maybe you have some model information. Well, in reality, typically you are going to actually only have approximate estimates of these gradients. But for simplicity, we're going to actually just assume we have exact gradient evaluation and focusing understanding the optimization dynamic under this situation. Okay, so there is actually one very nice paper by Agavo et al. Where they show, despite the non-concavity of this problem, softmax PG actually converge asymptotically to find the global optimal policy. However, it doesn't tell us how fast this algorithm converges. And this asymptotic convergence can be potentially very slow. To address this challenge, there is a follow-up paper by May et al. Where they try to pin down a finite time convergence guarantee for this algorithm, where they show softmax PG can find an epsilon optimal policy in a number of iteration scales like 1 over epsilon. However, their results have this interesting and unspecified dependency on problem parameters, which is unclear how it actually scales with respect to all the problem dimensions, like the size of the state action space and the effective horizon. So it's still not very conclusive whether this kind of asymptotic rate or this finite time rate is indeed a good rate, or in some situation it can get really bad or ugly. And to answer this question, we actually try to think from a lower bound perspective And we deliver this somewhat negative message for softmax policy gradient that tells you that you can actually, again, construct some sort of MDP where you can get it, even when you start from some kind of benign initial state distribution and assume exact gradient calculation, this algorithm may still take a number of iterations that scales as s to the 2th power to the other effective horizon, even to drive the error to some kind of constant level. So what this is suggesting is that even though the algorithm converges asymptotically, it can actually take a super exponential time to converge. And this is especially problematic when the problem has a very large state space along effective horizon. And this issue still persists even when you settle with a somewhat weaker goal that only tries to drive the average suboptimality gap small, rather than trying to drive the entry-wise error small. Without getting into the details of analysis, but right now we are kind of like at an intersection where we have this one algorithm, softmax policy gradient, which is probably the most natural algorithm to use. But we know there exist problems where this algorithm converges painfully slow. So the question becomes, can we actually take a better algorithmic approach? Right? Maybe we shouldn't be taking a pumpkin cart at the rush hour when traveling in New York City, but maybe we should find a subway to take. So what is a subway for us, for our problem? And it turned out that there's a better way to boost up the convergence. So the first booster we can take is to, instead of using the vanilla policy gradient, we can take natural policy gradient, which tries to leverage the curvature of the problem better and finding better search directions. So in that, instead of trying to search along the vanilla gradient direction, we're going to actually search along the direction that is preconditioned by the inverse of the Fisher information matrix that leverage the information from the parameterization of the policy. And this is first introduced into the literature reinforcement learning by Sham Kakadi back in 2002. And in fact, NPG is also can be thought as a backbone for a lot of the popular heuristic methods people use in modern IO these days, like TRPO and PPO, where you can essentially think of them as running NPG with line search to decide the learning rate. Another important booster that people leverage in practice is this so-called entropy regularization that tries to sort of promote the stochasticity of the policy along the trajectory of the algorithm. You can essentially think of this as a way to modify your loss function by adding in a regularization term, where instead of just having the reward in your value function, we're also adding in a term that looks at the entropy of the policy in use at every time, where the parameter tau is our regularization parameter. So instead of trying to optimize over the vanilla value function, now we can actually optimize over this regularized value function, and hoping that this regularization can actually help us to accelerate the convergence. So with these two ingredients in mind, let's look at how this can actually accelerate the convergence in a toy example. So this is a toy example with on a bandit problem, which is the most simple kind of IO problem with only one single state. And here we have 3 arms with different rewards, 1, 0.9, and 0.1. And so the first arm is the best. And if you're running a policy gradient on top of this, you are essentially working on the left top panel, where we see the algorithm actually kind of take a detour path to find the optimal policy. Now, if we move from the policy gradient to natural policy gradient to the right column, we see that we actually now allow ourselves to find a more direct path to the optimal policy, indicating indeed by using natural policy gradient, the algorithm can converge much faster. Now, similarly, if you increase amount of regularization in this problem, although we are also changing a little bit the objective, but we also see that the search path also tends to become more smooth and more direct to the optimal solution. indicating both of these two strategies help us to accelerate the convergence. So the question from a theoretical perspective is, can we actually justify the efficacy of this kind of entropy regularized NPG method used in practice? Indeed, we have a paper that try to answer this question for the tabular setting, where we see that, in fact, in this tabular setting, the update rule can be written down in a much simpler manner directly on top of the policy update, where you can think of the way we are updating the policy is essentially taking this multiplicative combination of the current policy in use and also kind of soft greedy version of the previous, the Q function of the previous policy. And interestingly, this update rule is actually invariant to the choice via initial state distribution. And if you take the largest possible learning rate, which is on the order 1 minus gamma divided by tau, you are essentially dropping the influence of your current policy. And this can essentially be thought as a soft version of the classical policy iteration algorithm because of the introduction of the entropy regularization. And for this algorithm, we actually were able to show it actually achieved a linear rate of convergence, where the iteration complexity of this algorithm is on the order 1/eta tau times some log 1 over epsilon, where epsilon is a final accuracy you want to achieve. So if you take the largest possible learning rate and look at the convergence rate of soft policy iteration, this actually matches with the convergence rate of policy iteration, the classical dynamic programming algorithm, which is actually an interesting connection that we'll highlight later. And what this result tried to highlight is essentially by leveraging this entropy regularization and natural policy gradients, we actually now have global linear convergence, where the convergence rate is almost independent with the size of the state and action space, which is also in sharp contrast with the earlier pessimistic message of softmax policy gradient, which may take exponential time to converge. Well, now we can probably say something much stronger with this new algorithm. So this is a little bit of a empirical comparison just to highlight the role of entropy regularization when you compare it with the vanilla NPG method, which already converge at a sort of dimension-free manner. But if you do not have any entropy regularization, the algorithm only converges at a sublinear rate on the order 1/epsilon. While when you have entropy regularization, it actually converges at a linear rate at log 1/epsilon. Care needs to be taken because here we are actually solving a slightly different problem when we have entropy regularization. But this sort of highlights why entropy regularization is used in practice to enable fast convergence. And it may also look somewhat similar to the effect of if you're adding in like a strong, quadratic regularizer to strongly convexify a convex problem, you will move from a sublinear rate to a linear rate. But here we are actually working with a highly non-concave problem. But we see something actually kind of have a similar taste to that kind of effect. From the theoretical analysis perspective, one of the interesting ingredient in our analysis for examining this kind of entropy regularized problem is that we actually identify this key operator that's called the soft Bellman operator, which can be thought as kind of a smoothed version of the original Bellman operator when we add in entropy regularization. And the nice thing with the soft Bellman operator is that it actually inherits some of the nice properties of the original Bellman operator, where the soft optimal Q function turns out to be the unique fixed point. And it also inherits this nice gamma contraction property. So with this in place, we can almost immediately write down the convergence guarantee of soft policy iteration by essentially duplicating the dance of the policy iteration, where you alternate between policy evaluation and gradification to this new algorithm, soft policy iteration. where you just replace the gradification step by this new soft gradification step and leveraging the nice property of the soft Bellman operator. Of course, in order to analyze the linear convergence in the full range of the learning rates, we need to do more work. But it turns out the analysis can be actually done also in a very concise manner, where the proof, I believe, is probably no more than 2 pages. So if you're interested in seeing the full proof, you can look at our paper that is published in Operations Research last year. All right, so with that, that sort of covers my story on policy gradient methods, highlighting the potentially pessimistic slow convergence of softmax PG, and also by leveraging entropy regularization and NPG, we can probably get a linear rate of convergence that is almost dimension-free with respect to the dimension of your MDP. So are there any questions that I can answer maybe quickly before I go to the last part of the talk? All right, so maybe because of time, let me quickly talk about the last part, which is our study on offline IL. So what is offline reinforcement learning? This may sound a little bit counterintuitive because typically reinforcement learning look at problem where you actually do active exploration in the environment. But there is a lot of new interest in this kind of offline setting because in a lot of applications, particularly in applications that are safety or privacy constrained, we may not be able to explore the environment as much as we want or generate new data. But on the other end, we may already stored a lot of historical data for us to use based on, for example, based on running maybe some kind of historical behavior policy. This is particularly the case, for example, in the medical domain, in the recommendation system domains or self-driving. So the question is it possible for me to learn a good policy based solely on the history data without doing any kind of active exploration? So to answer this question, let me also give you a little bit of mathematical model that we proposed or we leveraged to study this kind of offline IL problem. So let's start again from this sort of generative model. Earlier in the generative model, because we can have access to this generative model to generate new data, we can essentially probe any kind of state action pair we want to. However, this is no longer the case when we are dealing with offline IL because we cannot generate new data, but rather the state action pairs we can have access to is already predetermined by maybe some kind of behavior policy. So we can maybe imagine some genie maybe generate some pick the initial state according to some initial distribution. And then we have some behavior policies that generate action. And then only for this particular state action combinations, we will be able to inquire this transition kernel and see the next state. So if we can generate a history data based on this particular probabilistic model, we want to see whether we can actually find a good policy. Hopefully, maybe is up to some optimal accuracy, epsilon, in a sample efficient manner. So what is the particular challenges when dealing with this kind of offline IL setting, when in contrast to some of the earlier settings we talk about? So one of the challenge is that we can no longer have a uniform coverage over the entire state action space or hope for some kind of sufficient exploration when we can do active exploration. But rather in this kind of passive setting, we are confined with the capability of this historical data set where we have to deal with this kind of partial coverage that are induced by some behavior policy. And often this amounts to dealing with this so-called distribution shift between the distribution of the data set in hand versus the target policy, the target distribution that we actually are interested in, which should be induced by the optimal policy. And in order to capture this sort of distribution mismatch, people have proposed this so-called single policy concentrability coefficient, which try to measure essentially the distribution difference between the optimal policy pi star and the behavior policy pi b. And the way they measure this is using the so-called state action occupation density that look at essentially how well these policies are covering the entire state action distribution, state action space. And what is interesting with this quantity is that it can actually allow you to have scenarios where your behavior policy do not visit all the state action pairs as long as it visits all the state action pairs covered by your optimal policy. So in that setting, your C star, this quantity will be finite and your problem actually will be well posed. So this actually allows you to deal with scenarios where you actually only have partial coverage, which is one of the issues that is most difficult to deal with in offline IL. So let me try to maybe speed up a little bit. So one of the approach we are looking at here is this so-called model-based approach that try to first use the data to generate kind of empirical model and then plug this model into a dynamic programming oracle, hope that it can find a good policy for us. So however, again, because it's pool coverage issues and the sample limits, this doesn't really work well in this kind of offline setting because some of this entries in the model can be very poorly estimated. So in order to deal with this issue, people have proposed the so-called pessimism principle that essentially tries to add in this kind of lower confidence bounds into the iterations of the value iteration algorithm, so that we can act more conservatively with respect to the estimates output by over the iterations. And with this value iteration LCB algorithm in place, there are some previous analysis for this algorithm. As what we are showing in the slide right now. However, these results still have a considerable gap from the minimax lower bound, where we see some of the previous algorithm only achieve the minimax lower bound until the sample size is quite large. So the natural question is, can we actually develop algorithm that actually match with the minimax lower bound? It turned out that with some careful analysis and more careful construction of the pessimistic penalty term, we can actually show this kind of value iteration in conjunction with the LCB can actually achieve the minimax lower bound over the entire range of the sample complexity and the entire range of the accuracy range. So if you put this back into the picture, we see that actually this model-based reinforcement learning algorithm is minimax optimal for this offline setting with no burn-in cost. So that means the algorithm is optimal over the entire range of sample complexity of interest. So with all this in place, let me just quickly conclude this talk. So hopefully, with the three examples I illustrated over the three most popular approaches in reinforcement learning, value-based, policy-based, and model-based, I was able to deliver a little bit of flavor in terms of some of the results we have in understanding non-asymptotic performance guarantees of reinforcement learning algorithms. And I hope I convey that this is actually the right audience to work on such problems, because there are actually a lot of interesting mathematics in these problems that we can leverage a lot of the mathematical arsenals in statistics, optimization, control, and shed some light on some of this very popular heuristic algorithm reinforcement learning that to a large extent are still not very well understood and stay as heuristics. There are a lot of interesting future directions. There's just a lot of interesting formulations in RL, like robust RL, multi-agent RL, and last but not least, also function approximation. In this talk, I have constrained with the setting of tabular setting, But in practice, all the problem has neural networks in it. People do new function approximation all the time. And actually understanding function approximation in the context reinforcement learning is a very interesting topic as well. So if you're interested in looking at some of the papers, you can find them on my website. And here are some of the references. With this, I would like to conclude. I'll be happy to take any additional questions that you may have. Thank you so much for listening.
Thanks a lot for a great talk. So I'll cut the recording here, and then we can maybe ask any other questions that folks might have.